65 years, billions of frequency channels, 1 million of the nearest stars checked and rechecked by the largest instruments our species has ever built. And in all of that time, the total confirmed haul is one signal on one night in 1977 that lasted 72 seconds and never came back. Meanwhile, the arithmetic says this galaxy should be crowded. Thousands of civilizations, possibly millions, transmitting right now in this galaxy tonight. Something is producing that gap, and there are roughly 30 serious explanations for it. We're going to go through all of them. The comfortable ones first, then the ones that are harder to shake off, and when the ones that fail have been set aside, one is left standing. By the end of tonight, you will know exactly what it is, and why the people who study this for a living tend not to say it out loud. Settle in, subscribe if you haven't already, and stick around, because the reason that last explanation is so hard to accept has nothing to do with the sky, and everything to do with the century we happen to be standing in. Let's get into it. Part 1. The question at the lunch table. There is an answer to the Fermi paradox. Not a guess, not a mood, not one of those ideas that sounds profound at 2 a.m. and falls apart by breakfast. An answer that holds together when you run the arithmetic, when you line it up against the observations, and when you follow the logic all the way to the end without looking away. Most of the researchers who have spent their careers on this question know what it is. A few of them will say it out loud, most will not, and not because they think it is wrong, because of what it means. It means something very specific about us, and about right now, and about the particular century we happen to be standing in. We're going to work our way there properly. There are roughly 30 serious explanations for why the universe is quiet, and we're going to go through them, starting with the comfortable ones, moving into the ones that are harder to shake off, and ending with the ones most people stop reading before they finish. And when all of them have been laid out and tested against what we actually see, one is left standing. That is where tonight goes. But to understand why that answer is so difficult to accept, you have to understand the question, the real one, not the poetic version. And the real one was asked, almost as a throwaway line, over lunch in the summer of 1950, Los Alamos, New Mexico. The war has been over for 5 years. Enrico Fermi is visiting, and he walks to lunch with 3 colleagues, Edward Teller, Emil Konopinski, and Herbert York. On the walk, the conversation drifts to something in the newspapers that week. Flying saucers, sightings everywhere. Somebody mentions a cartoon that had run in the New Yorker, which had cheerfully blamed a rash of missing municipal trash cans on extraterrestrials hauling them off into space. There is laughing. The men sit down. The conversation moves on to other things entirely, the way lunch conversations do. And then, some minutes later, out of the middle of nothing, Fermi looks up and says almost casually, "But where is everybody?" His colleagues laughed. Then they stopped laughing because they realized he was not joking, and because they realized he had been doing arithmetic in his head, while the rest of them were talking about something else. All 3 of them wrote down their memories of that lunch decades later, and their accounts disagree in the details. Teller remembered a specific probability attached to it. York remembered a longer chain of reasoning delivered out loud, step by step, in Fermi's usual style. What none of them disagreed about was the substance. In the space of a few minutes, Fermi had estimated how many technological civilizations ought to exist in our galaxy, compared that estimate to the total quantity of evidence for even one of them, and found the gap unacceptable. He never published it. There is no Fermi paper on this. It circulated as an anecdote among physicists for the better part of 20 years, before anyone attached his name to it as a formal problem, and the name it eventually got is arguably wrong. It is not a paradox in the strict sense. It is a collision between what the numbers predict and what the sky delivers. That collision has now been open for 76 years, and in that time it has not narrowed. It has widened, and every major instrument we have built has widened it further. The formalization came 11 years later, in a small room in West Virginia. In November of 1961, an astronomer named Frank Drake convened a meeting at the National Radio Astronomy Observatory in Green Bank. 10 people were invited. Carl Sagan was there, early in his career. Philip Morrison was there. So was Melvin Calvin, who learned partway through the meeting that he had just been awarded the Nobel Prize in Chemistry, which is the kind of thing that happens at meetings like that one. Otto Struve, who ran the observatory, was there. Drake needed an agenda, so he stood at the blackboard and wrote one, in the form of a chain of terms multiplied together. Not because he thought the product would be a meaningful number, but because the terms, taken in order, happened to be a complete list of every question you would have to answer in order to know. You start with how many stars are being born, then you ask what fraction of them have planets, then how many of those planets on average could support life, then of those how many actually get life, then how many of those get life that becomes intelligent, then how many of those intelligences build something that broadcasts, and then, last, the term Drake himself would spend the rest of his life saying was the most important one: how long a civilization like that keeps broadcasting before it stops. Drake's own point, repeated for 60 years to anyone who would listen, was that the equation is not a calculator. It is a way of organizing what you do not know, and in 1961, essentially every term in it was a shrug. We did not know whether planets were common. We did not know whether life was likely. We were estimating in the dark, and everyone in that room knew it. We are not estimating in the dark anymore, and that is the single most important development in this entire story. The Kepler Space Telescope ran from 2009 to 2018. It stared at a single patch of sky containing about 150,000 stars and watched for the almost imperceptible dimming that happens when a planet crosses in front of one. It confirmed more than 2,600 planets by itself, and it established something far more consequential than any individual discovery. Planets are not rare. Planets are the normal outcome of star formation. There are more planets in this galaxy than there are stars. Across every method we now use, the confirmed count of worlds around other suns has passed 5,900, and the confirmed count is a rounding error against the real population. Rocky planets in the temperature range where liquid water can sit on a surface are less common, but not exotic. Depending on how strictly you define your terms, somewhere between a few percent and roughly a fifth of sun-like stars have one. So take Drake's chain, drop in the measured values for the first terms, and be deliberately stingy with the ones we still cannot measure. Assume life is hard. Assume intelligence is harder. The number you get out the other end is somewhere between thousands and millions of communicating civilizations in the Milky Way, right now, not spread across all of time, but currently, simultaneously, potentially detectable. That is one galaxy. There are around 2 trillion more, which means the sky should be loud. It should be full of transmissions, of stray leakage, of the industrial fingerprints of technology, of construction on scales we would have to work hard to overlook. At an absolute minimum, in 65 years of pointing sensitive instruments upward, we should have tripped over something by accident. And here is the piece of context that should sit underneath everything that follows tonight. We have been a radio-detectable species for about 100 years, a century, against a galaxy that has been in the business of building stars and planets for 10 billion. We are not a long-running experiment. We are a single frame, and we are trying to work out what the whole film looks like from inside it. So what have we actually heard in all that time with all those instruments? There is one entry on that list. One. And a man wrote a single word next to it in red pen and then spent the rest of his life being asked about it. Part 2. One word in the margin. The search started with 2 stars. In the spring of 1960, before the Drake equation existed, Frank Drake pointed an 85-foot dish at Greenbank toward Tau Ceti and Epsilon Eridani, the 2 nearest sun-like stars, and listened near 1420 MHz for about 200 hours across several months. He called it Project Ozma after the princess in the Oz books, on the reasoning that Oz was a faraway place populated by strange beings. On the first morning he got a strong signal, and briefly thought he had done it in the first hour of the first day. It turned out to be a passing aircraft. The rest of the 200 hours produced nothing. That is where this began. It has not stopped since, and the scale of what came after is worth having in your head before anyone tells you we have not looked. In the mid-1980s, Paul Horowitz at Harvard built a machine called Meta, funded in part by Steven Spielberg, who wrote a check because he thought the question deserved an answer. Meta could listen to 8.4 million frequency channels at once and swept the entire northern sky. At Berkeley, a program called Serendip took a different approach entirely. It does not ask for telescope time. It attaches itself to whatever a large radio telescope is already doing and listens in parallel across billions of channels wherever the dish happens to be aimed. It has been doing that since 1979, and when the data volume outgrew the computers, the project simply handed it to the public. SETI at home ran from 1999 to 2020 and distributed the analysis across more than 5 million volunteer machines, which for a period made it one of the largest computing efforts our species had ever assembled. Then, in July of 2015, the scale changed again. Yuri Milner committed $100 million of his own money to a program called Breakthrough Listen. Not a government grant. A private individual writing a check because he wanted the answer badly enough to pay for it himself. Breakthrough Listen bought dedicated time on the Greenbank Telescope in West Virginia, on the Parkes Telescope in Australia, and later on the Meerkat Array in South Africa. Its targets are the 1 million nearest stars, the plane and centre of our own galaxy, and the 100 nearest galaxies, across frequencies from roughly 1 to 10 GHz, a band that includes essentially every channel physics suggests would be efficient for talking across interstellar distance. 65 years, billions of channels, millions of stars, volunteer computers in 5 million living rooms, and the entire confirmed result of all of it is 0. There is one entry in the anomaly column, and it is from a night in 1977. The Big Ear radio telescope at Ohio State University was not a dish. It was a flat field of aluminum and a pair of enormous reflectors, and it did not track. It could not swivel to follow a target across the sky. It simply stared at a fixed strip and let the rotation of the Earth carry the universe past it, which means that if a genuine point source out there had crossed the beam, it would have appeared, risen in strength, peaked, and faded over a window of exactly 72 seconds. Not approximately 72, exactly. That number was a prediction, written into the geometry of the instrument before anything was ever detected. On the 15th of August 1977, the telescope recorded a narrow band signal at roughly 1420 MHz. That frequency is the hydrogen line, the resonance of the most abundant substance in the universe, and it had been proposed 18 years earlier by Giuseppe Cocconi and Philip Morrison as the obvious channel any civilization might choose precisely because everyone everywhere would know where to find it. Imagine you are Jerry Eman a few days later. You are a volunteer. You're sitting at your kitchen table with a fanfold computer printout, a paper roll of single characters, each one standing for how strong the signal was in that channel during that interval. Most of the page is ones and twos and blanks, which is what background noise looks like when you write it down. You're running your eye down the columns the way you have done 100 times, and you find a sequence that does not belong there. 6, E, Q, U, J, 5. In this encoding, once the intensity climbs past 9, the machine switches to letters. E is 14, Q is 26, U is 30 times the background. You sit there for a moment with the paper in your hands, and then you take a red pen and you draw a circle around those 6 characters, and in the margin beside it you write one word. Wow. It has never come back. Big Ear went back to that patch of sky more than 50 times. The Very Large Array searched it. Meta searched it. In the 49 years since that night, that region of Sagittarius has been examined again and again by multiple instruments across multiple decades, and the signal has never returned, not once, not faintly. And nobody has explained it away either, which is the part that keeps it alive. Satellite reflection was considered and does not fit. Terrestrial interference does not produce that clean horizon fall over exactly the transit window. In 2017, someone proposed a hydrogen cloud around a passing comet, and that explanation was criticised fairly quickly on the grounds that comets do not produce narrow-band emission of that character, and that the comets in question were not in the right place at the right time. A reanalysis in 2024 suggested something more interesting, that a cold hydrogen cloud might have been stimulated into brief emission by a transient burst from something like a magnetar. That is a natural explanation, and it might be right, and it remains unconfirmed. Sit with the shape of that for a moment, because it is the emotional centre of this entire subject, and it is not the signal itself. For 49 years our species has been going back to the same doorway, not once, not out of nostalgia. Systematically, with successive generations of instruments, some of which cost more than the entire economy of a small country, we have returned to one patch of sky and pointed at it and waited, and nothing has happened, and then we have done it again. There is something almost unbearably human in that. The great silence is usually described as emptiness. It is not emptiness. It is attention, repeated, unrewarded, for half a century. The big ear itself is gone. Ohio State demolished it in 1998 to extend a golf course. The most famous detection in the history of the search for other minds was made by an instrument that was torn down for a fairway. So that is the state of the evidence, one anomaly in 65 years, at exactly the frequency the theory predicted, that appeared once and was never repeated. And an arithmetic that says the sky should be crowded. Hold on to that word in the margin, because we are going to come back to it much later tonight, and when we do, the fact that it never happened again is going to look like a very different kind of fact than it looks like now. But before any of that, there is an obvious objection, and it is the first thing almost everyone says. Maybe the problem is not out there. Maybe the problem is us. Maybe we have been listening for the wrong thing, in the wrong way, with instruments too crude to catch what is actually being said. That objection is better than it sounds. It is also not good enough, and understanding exactly where it breaks is what starts closing the doors. Part 3. The comfortable exits. The most comfortable explanation is the one that lets you sleep, and it goes like this. The signals are there. We are simply looking in the wrong place, at the wrong frequency, with the wrong instruments. We are like somebody trying to find a radio station by tapping on the walls. I want to give that argument its strongest possible form, because the weak version is easy to knock down and the strong version is genuinely unsettling. The strong version does not come from astronomy. It comes from information theory, and it starts in 1948 with a paper by Claude Shannon called A Mathematical Theory of Communication. Shannon was working out the mathematics of how information moves through a channel, and one of his results is not a hypothesis or an interpretation, it is a theorem. A perfectly compressed signal is statistically indistinguishable from random noise. Think about what that actually means, because it is stranger than it sounds. The thing that makes a signal look artificial to us is redundancy, patterns, repetition, a carrier wave that sits at one frequency, a pulse that arrives on a regular beat, a string that repeats. All of that redundancy is, from an engineering standpoint, waste. It is capacity you're not using, and the entire history of communications technology is the history of squeezing that waste out. The better you get at transmitting information, the less structure your transmission has, until at the theoretical limit it has none at all, and what comes out the antenna is a stream that to anyone without the decoding key looks exactly like static. We are detectable precisely because we are bad at this. Our broadcasts are sloppy. They carry enormous redundancy. They sit on fixed carrier frequencies and repeat themselves relentlessly, which is why an outside observer with a decent receiver could pick out a 1950s television transmission from 100 light-years away and know instantly that no natural process made it. A civilization a million years ahead of us would not be doing that. Not because it is hiding, because it has better engineers. Lachman, Newman and Moore made this argument explicitly for the search in 2004, and John Smart pushed it further in 2012, arguing that advanced civilizations converge on inward, dense, efficient development rather than sprawling outward, and become quiet as a side effect of getting good at things. And we already have a working demonstration on this planet. Spread spectrum encoding, which underlies the satellite navigation in your phone, and a great deal of military communication, deliberately smears a signal across a wide band so that it sits below the noise floor and looks like nothing at all unless you know the key. We invented deliberately noise-like transmission within a single human lifetime of inventing radio. Now extend that trend by 1,000,000 years and ask what the sky would sound like. There is another version of the same problem, and it is about geometry rather than encoding. Claudio Macconi, working on the optical and infrared side of the search, has pointed out that a mature communications network would not broadcast at all. It would use tightly focused beams between endpoints that already know where each other are. The same information moves. Nothing leaks sideways. From any other angle in the galaxy, a civilization running a laser network is not quiet by choice. It is quiet by optics. And then there is the genuinely humbling part. The channels we did not possess. On the 14th of September 2015, the LIGO detectors registered a ripple in the fabric of space-time produced by two black holes merging roughly 1.3 billion light-years away. That was the first gravitational wave humanity ever detected. Before that morning, gravitational wave astronomy did not exist. Not as an underfunded field. It did not exist. If something had been modulating gravitational waves for a message before 2015, we would not have missed it through inattention. We would have missed it because we had no organ capable of perceiving it. Neutrino astronomy is barely out of its infancy. Neutrinos pass through matter almost without interacting at all, which makes them a nearly perfect long-distance carrier, and we have detected exactly one burst of them from a supernova, and essentially never looked for artificial structure in them. What else is there? Modulated channels in physics we have not discovered yet? The honest answer is that we do not know, and not knowing cuts in both directions. It means the silence might not be silence. It also means we cannot use it as a full explanation, because we cannot build an argument on an unknown. There is one more assumption buried in the search that is worth naming out loud. The band our instruments have concentrated on, the stretch between the hydrogen line and the hydroxyl line that radio astronomers affectionately call the water hole, was chosen partly because it is quiet and partly because the chemistry of water is a poetic common ground. It is a good choice. It is also a choice that assumes the sender is deliberately dumbing down a transmission so that a beginner can find it. That is a large assumption to build 65 years of searching on top of. But here is where this whole family of explanations runs into a wall. And the wall is simple enough that it does not require any information theory at all. None of it requires anyone to be talking to us. A civilization does not have to send a message to be visible. It has to use energy. And every use of energy ends by the second law of thermodynamics as low-temperature heat radiated into space. There is no way around that. It is not an engineering choice. Back in 1960, Freeman Dyson pointed out the consequence. A civilization that captured a large fraction of its star's output would appear as an object that is strangely dim in visible light and strangely bright in the mid-infrared, in a way that no natural object produces. That is not a message. That is a thermodynamic receipt, and it does not care whether anyone wants to be found. We have looked. Infrared surveys from eras in the 1980s, through WISE, and now with the James Webb Telescope, have been combed for exactly that signature. A survey called G, run out of Penn State, examined roughly 100,000 galaxies for the infrared excess you would expect if any substantial fraction of a galaxy's starlight were being intercepted and re-radiated. Nothing. A project called Hephaestos published a handful of candidate red dwarf systems in 2024, and every one of them so far is consistent with something ordinary, a dust disk or a background galaxy sitting in the wrong place. Then there are atmospheres. Industrial activity changes the chemistry of an atmosphere in ways that persist. The James Webb Telescope reads exoplanet atmospheres now, routinely, and it can in principle detect molecules like chlorofluorocarbons, which have no natural production route whatsoever. Dozens of atmospheres characterized. Nothing. And there was one spectacular near miss. Tabby's star, catalogued as KRC 8462852, produced deep, irregular, aperiodic dimming events that briefly made megastructures look like a live hypothesis. Then somebody measured the dimming at multiple wavelengths and found that it was wavelength dependent, which is precisely what dust does and precisely what a solid opaque object cannot do. That door closed. So put the two halves together, we might be missing the conversations, we are not missing the buildings, and we do not see any buildings. When you check for something through many independent channels at once and every single one of them returns nothing, the usual conclusion is not that your instruments are bad, it is that the thing is not there, which means the silence is not an absence of effort. It is a result, and results have causes, so if the explanation is not that we are looking wrong, the next one in line is gentler and older, and for a while it seems to work beautifully. Maybe they were here. Maybe we simply arrived after everyone else had already gone home. Part 4. The Ones Who Came Before. Here is the gentler version of the silence, and it is the one I find people reach for once the first explanation stops working. Maybe they were here, just not now. The universe is 13.8 billion years old. Our solar system is 4.6 billion. That leaves an enormous amount of time in which things could have happened without us, and it is entirely reasonable to wonder whether we simply showed up during an intermission. The numbers behind that idea are real, and they are worth walking through, because the early universe was not a place where any of this could have occurred. The first generation of stars formed somewhere around 100 to 200 million years after the beginning, and they were made of essentially nothing but hydrogen and helium. That is the entire inventory the Big Bang left behind. No carbon, no oxygen, no nitrogen, no iron, no silicon, no phosphorus. None of the heavier elements that rocky planets are built out of and that biology is assembled from. Every atom of calcium in your bones and every atom of iron in your blood had to be manufactured inside a star and then scattered by that star's death before anything like you was chemically possible. That process takes time, and it takes generations. The earliest stars that could plausibly have hosted an Earth-like planet formed somewhere in the neighbourhood of 9 to 10 billion years ago, which means there were suns with rocky worlds around them for 4 or 5 billion years before our sun existed at all. 4 or 5 billion years is not a head start. It is an entire separate history, long enough for civilizations to arise, mature, spread, and disappear several times over, and for their ruins to be worn down into geology. And what does a civilization look like after 1 billion years? Consider what we would leave. We have had writing for about 5,000 years, metal tools for maybe 10,000. We have existed in something like our current form for 200,000. 1 billion years is 5,000 times the entire span of anatomically modern humans. The geological record on Earth from 1 billion years ago is fragmentary in the extreme. Some rock, some minerals, some chemical anomalies in ancient strata, and vast stretches where the record simply does not exist because the crust that carried it was recycled back into the mantle. A city does not survive that. A monument does not survive that. Even a continent barely survives that. So the timing explanation has real teeth. It is not a hand wave, and it comes with a mathematical companion. In 1993, the Princeton astrophysicist J. Richard Gott published an argument in Nature, applying the Copernican principle to the question of how long we should expect our own species to last. His reasoning was that there is nothing special about the moment at which you happen to observe something, and if you plug our current run of roughly 200,000 years into that logic, you get a 95% confidence range for our remaining future of somewhere between about 5,100 years and 7.8 million. Wide, but bounded. Apply the same reasoning across a galaxy of civilizations that each last some finite time and are separated by thousands of light years, and the odds that any two of them are transmitting simultaneously in each other's direction within the light travel time between them become extremely small. Signals cross the galaxy constantly. They just do not arrive when anyone is home. There is a way to feel that overlap problem rather than just calculate it. The light arriving at your eye from the Andromeda Galaxy tonight left its source about 2.5 million years ago. When it set out, our ancestors were walking around the African savannah with stone tools and no language. Every single thing that has ever happened in human history has happened while that light was in transit. Now suppose somebody in Andromeda pointed a transmitter at this galaxy on the day that light departed. That signal is already here. It arrived at some point during the last 2.5 million years, and for 2.5 million minus about 70 of those years, there was nobody on this planet with an instrument capable of noticing. The message would have washed over the Earth and kept going, and the civilization that sent it would very likely have been gone for 1 million years by the time we built the receiver. Stephen Webb, who has spent 2 editions of a book cataloguing every proposed resolution of this problem, works through the arithmetic of contact windows in detail. Take any reasonable assumption about how long a civilization lasts, spread those civilizations across a galaxy 100,000 light-years wide, and require that 2 of them be alive, transmitting, and pointed at each other within the light travel time between them. The probability that any given pair ever manages it falls to a fraction of a percent. The galaxy could be full of conversation, and every line still be busy at the wrong moment. And I want to be honest, that argument works. It genuinely accounts for the radio silence. It does not account for the rest of it, and this is the point where the explanation quietly breaks in half. Because civilizations do not only leave ruins, they leave engineering, and engineering leaves thermodynamic and chemical traces that persist on timescales that make cities look like weather. Go back to Dyson's argument. A structure built to intercept a star's output radiates that energy back out as infrared. It does that whether the builders are alive or not. If the swarm is still there, the star still looks wrong, too dim in the visible, too bright in the infrared, in a pattern that no natural stellar process reproduces. That signature does not decay when the civilization does. It decays when the structure does, which for orbiting material could be an extremely long time. Atmospheres are the same story from a different direction, and this one is genuinely striking. Earth's atmosphere has been visibly, unmistakably altered by life for something on the order of 2 billion years. The oxygen you are breathing is thermodynamically unstable. It should not be there. Oxygen and methane coexisting in the same atmosphere is a chemical impossibility over geological time unless something is constantly replenishing both, and that something is biology. If every living thing on this planet stopped tonight, that signature would take millions of years to fade, not thousands. And the James Webb Telescope can read exactly that kind of chemistry across light years, right now, and is doing it on world after world. So the silence is not just an absence of active transmission, it is an absence of residue, and residue is much harder to explain away, because it does not require anyone to still be there. Picture a house that has clearly been lived in for a very long time, by many families, over many generations. Now walk into it, and find not just that nobody is home, but that there is no dust on any surface, no wear on any stair, no marks on any doorframe. That is not an empty house. That is a swept one, and the sweeping is the thing that needs explaining. Which forces the question back a step. If they did not come and go, maybe they never got started. Maybe the problem is not that civilizations end. Maybe it is that almost nothing ever becomes complicated enough to be called one, because the list of things that have to go right first is longer than almost anybody expects. Part 5. The Requirements List. In the year 2000, 2 researchers at the University of Washington published a book with a title that has been doing damage to comfortable assumptions ever since. Peter Ward is a paleontologist, a man who has spent his working life reading mass extinctions out of rock. Donald Brownlee is an astronomer, one of the people who built the mission that flew through a comet's tail and brought material home. Between them they had the 2 halves of the problem, and the book they wrote together is called Rare Earth. Their argument is more careful than the way it usually gets summarized, so let me state it precisely. They are not saying life is rare. They expect microbial life to be common, possibly extremely common, possibly on worlds inside our own solar system. What they are saying is that complex life, the multicellular, differentiated nervous system having kind, requires a conjunction of conditions, each of which is individually uncommon, and that multiplying uncommon things together gets you to vanishing rather quickly. Let us actually go through the list, because it is longer than most people expect and each item is stranger than the last. Start with where you are in the galaxy. We're used to the idea that a star has a habitable zone, a band of orbital distance where water can stay liquid. The galaxy has one too. Move too far inward toward the crowded centre, and you're sitting in a neighbourhood with a much higher density of stars, which means a much higher rate of nearby supernovae, much more radiation, and far more gravitational disruption of whatever reservoir of comets your system has parked in its outskirts. Move too far outward, and the interstellar gas your star formed from is too poor in heavy elements to build a rocky planet in the first place. Earth sits about 26,000 light-years from the galactic centre, in a comparatively quiet stretch between spiral arms. The concept has a name and a paper. Gonzalez, Brownlee and Ward formalised the galactic habitable zone in 2001, and like every other item on this list it has been argued about ever since. But the basic geometry is not really in doubt. There is an inner boundary set by violence, and an outer boundary set by chemistry, and the band between them is a minority of the galaxy's stars, not a majority. Second, the star itself. And this is where the numbers turn uncomfortable, because red dwarfs make up somewhere around 70 to 75% of every star in the galaxy. They are small, cool, and extraordinarily long-lived, which sounds ideal until you look at what actually happens near one. Red dwarfs are magnetically violent, especially when young. They throw flares that are enormous relative to their size. In 2019, Proxima Centauri, the nearest star to our own, produced a flare that brightened it by a factor of thousands in a matter of seconds, and any planet in its habitable zone would have had its ozone stripped and its surface bathed in ultraviolet. And because a red dwarf is faint, its habitable zone sits so close in that a planet there is almost certainly tidally locked, one face permanently toward the star, one face permanently in the dark, with everything that implies for climate. Our Sun is a G-type star. That is under 10% of the stellar population, and even among its own class it is unusually quiet. Third, and this is the one nobody expects, Jupiter. 318 times the mass of Earth, parked out past the asteroid belt, doing something to the inner solar system's impact history for 4 billion years. The traditional version of this argument is that Jupiter acts as a shield, sweeping up or flinging away objects that would otherwise have found us. The honest modern version is messier. Some simulations suggest a giant planet in that position also injects material inward that would not otherwise have come. What is not in dispute is that the presence or absence of a giant planet and its exact orbit comprehensively reshapes what hits a small rocky world over billions of years. Whether that is protection or bombardment depends on the configuration, and the configurations are not all equally survivable. Fourth, the Moon. Ours is enormous relative to its planet. That is not normal for a satellite, and the reason it matters has nothing to do with tides, and everything to do with tilt. Earth's axis leans about 23.5 degrees, and it stays there, wobbling only slightly, because the Moon's mass holds it steady. Without that, our tilt would wander chaotically over tens of thousands of years. We can watch this happen elsewhere. Mars, which has 2 small captured rocks for moons, has undergone obliquity swings of tens of degrees, and its climate history is correspondingly violent. Complex life needs long stretches of relative stability, and the Moon is why we got them. Fifth, plate tectonics. Earth's crust is broken into moving plates that are constantly being subducted and recycled, and that process drives something called the carbonate-silicate cycle, which is best understood as a thermostat with a very long response time. Carbon dioxide gets pulled out of the atmosphere by weathering, locked into rock, carried down into the mantle, and returned through volcanism. When the planet warms, weathering speeds up and pulls more carbon out. When it cools, weathering slows and carbon accumulates. That feedback has held Earth's surface temperature inside the habitable range for 4 billion years, while the Sun itself brightened by roughly 30%. Think about that. Our star has become a third more luminous since life began, and the planet compensated. Venus has no plate tectonics, Mars lost whatever it had early, and there is a natural experiment sitting right next door that makes this point better than any simulation. Venus and Earth started with broadly similar bulk composition, similar size, similar distance from the same star. One of them has oceans, a biosphere, and a thermostat. The other has a surface hot enough to melt lead under an atmosphere 90 times heavier than ours. 2 nearly identical starting conditions, 2 completely different outcomes, and we still cannot fully explain the divergence. If the window is narrow enough that 2 neighbouring worlds fall on opposite sides of it, the window is narrow. The faint young sun problem is worth pausing on too, because it is unresolved and it is the kind of thing that should make anybody cautious about assuming these outcomes are robust. A third less sunlight 4 billion years ago should have left this planet frozen solid. It was not frozen. The usual explanation is a very different early atmosphere, thick with greenhouse gases, but the details do not close cleanly, and nobody has a fully satisfying account of why the young Earth was warm. Something about the setup was forgiving in a way we do not yet understand, and forgiving setups are not something you can assume elsewhere. Sixth, a magnetic field. Earth's liquid outer core churns and generates a dynamo, and that field deflects the solar wind, the steady stream of charged particles that would otherwise strip an atmosphere away molecule by molecule over geological time. Mars's dynamo shut down somewhere around 4 billion years ago. The MAVEN spacecraft has been measuring the consequence directly. Mars is still losing its atmosphere to the solar wind right now, and its surface pressure is already under 1% of ours. Now, multiply. The right position in the galaxy, the right kind of star, a giant planet in a survivable configuration, a large stabilizing moon, active crustal recycling, a working dynamo, and that is before a single biological requirement has been named. I want to be fair to the objections here, because this argument is genuinely contested and the criticisms are serious. Rare earth reasons from exactly one example. The claim that complex life needs precisely what Earth has is very difficult to falsify when you have no counterexamples to check it against. Some of the specific pillars have weakened under closer modelling, particularly the Jupiter shield and to a lesser extent the Moon. And tidal locking may not be the killer it once looked like, since a thick enough atmosphere can move heat around a planet efficiently. But the shape of the objection survives all of that. The number of independent conditions is large, and when you multiply uncertain probabilities across a long list of independent conditions, you get to very small numbers very fast, whether or not you trust any individual term. That is the stage, though. All of it is stage, and the play still has to happen. Because you can build the perfect world, around the perfect star, shielded by the perfect neighbour, and something still has to cross the line from chemistry into biology. And when you look closely at how that went here, on the only planet we can actually examine, the picture gets considerably worse. Part 6. The step that happened once. There is a step in this story that almost everyone skips over, including people who should know better. We talk about habitable zones and liquid water and the right chemistry as though the presence of ingredients implies the arrival of a cook. But between the ingredients are here and something alive is here, there is a gap. And that gap is one that no laboratory on this planet, with every advantage of intention, funding, and modern instrumentation, has ever successfully crossed. The transition from complex chemistry to the first self-replicating molecule is called abiogenesis, and it remains one of the deepest unsolved problems in science. We know roughly what the early Earth was like. We know a great deal about what molecules were available. We have a leading candidate for where it happened. Alkaline hydrothermal vents on the ocean floor, where mineral chimneys full of tiny pores sit at the boundary between acidic ocean water and alkaline fluid welling up from below. Across those thin mineral walls there is a natural proton gradient, and a proton gradient across a thin membrane is exactly, precisely, the mechanism that every living cell on Earth still uses to make energy right now, including yours, in the mitochondria in the muscle of your arm. Nick Lane, a biochemist at University College London, has built a career on that observation, and his 2015 book The Vital Question is the most serious attempt anyone has made to work out the details. His position is not that the origin of life was a miracle. It is that it required a very specific and demanding set of circumstances, and that those circumstances may not be common even on worlds that look otherwise perfectly habitable. There is one genuinely encouraging piece of evidence here, and I want to give it its due, because I will be spending the rest of this part making you uncomfortable. Life appears in the terrestrial record remarkably quickly. Within a few 100 million years of the surface cooling enough to hold liquid water, something was already alive. If the first step were nearly impossible, you would expect it to have taken most of the available time. It took almost none of it. That is a real argument that step 1 is not the bottleneck. Which brings us to step 2, and step 2 is the thing that keeps people awake. Roughly 2 billion years ago, in shallow water somewhere on a young Earth, one single-celled organism engulfed another and did not digest it. Let me put you down there for a moment. You're at a scale where the water is not a liquid so much as a crowded traffic system. Everything around you is bacteria, uncountable, ancient, extraordinarily good at what they do, and completely uninterested in becoming anything else. They have been running this planet unchallenged for well over 1 billion years. Then one cell folds its membrane around another. This happens constantly. It is how one of these things eats. The membrane closes, the interior chemistry gets to work, and normally, invariably, the passenger is dismantled into parts. Except this time it is not. This time the passenger keeps functioning inside its host. It keeps its own genome. It keeps its own machinery. It goes on producing energy, and the host, instead of digesting it, keeps it. Two organisms that had been separate for 1 billion years become one organism with 2 sets of instructions, and neither of them ever separates again. That thing became the mitochondrion. It is inside every complex cell that has ever existed on this planet. It still has its own circular DNA, its own ribosomes, and it still divides on its own schedule, which is why nobody seriously disputes where it came from. You can look at it under a microscope and see the evidence of an independence it has not had for 2 billion years. Every animal, every plant, every fungus, every organism on Earth with a nucleus, from the yeast in bread to the neurons you're using to follow this sentence, descends from that one merger. And here is the part that matters, and it is not the biology. It is the statistics. It happened once, not twice, not 100 times. Once in roughly 4 billion years of biology, on a planet absolutely saturated with bacteria, in an environment where the opportunity to try was effectively unlimited. There are more bacterial cells in a handful of garden soil than there are stars in this galaxy. Every one of them a trial, every generation another set of trials, generation after generation, for 1 billion years before it happened and 2 billion years since, and in all of that it has never happened again. That is not the profile of a difficult step. That is the profile of something that, given nearly infinite opportunity on a single world, only barely occurred at all. Sit with that for a second, because I think it is the single most unsettling fact in biology. The gate between a world with bacteria on it and a world with anything on it capable of wondering about other worlds may be the narrowest passage in nature, and we are standing on the far side of it, made entirely out of the descendants of one accident, with no idea why it worked here and apparently nowhere else. Compare it to what came after, because the contrast is the whole argument. Multicellularity, the thing we tend to think of as the big leap, evolved independently more than 20 separate times once eukaryotes existed. 20. That is what an easy step looks like. It happens repeatedly, in different lineages, without much fuss. The eukaryotic cell happened once and then never again, and everything complex that has ever lived is standing on it. The rest of the ladder is not free either. Oxygenic photosynthesis and the great oxidation event around 2.4 billion years ago had to happen before anything large could breathe. The Cambrian explosion, when most modern animal body plans appeared, is only about 538 million years back. Nervous systems, then large brains, then sociality, then language, then metallurgy, then radio. Each of those transitions took enormous spans of time under conditions we still do not fully understand. Brandon Carter turned this into a formal argument called the hard steps model. If the path to intelligence involves a small number of steps that are each individually improbable within the lifetime of a star, then the expected number of civilizations collapses, and something else follows. The striking near coincidence between how long intelligence took to appear here and how long our sun has left stops being a coincidence and becomes a selection effect. We were always going to find ourselves close to the deadline because anywhere it took longer, the star ran out first. That model has been challenged recently, and the challenge is worth knowing. A 2025 reassessment by Mills, McAlady, Frank and Kakar argued that the timings may reflect planetary gating rather than improbability. On that reading, the steps were not lottery tickets at all. They simply had to wait until the planet's chemistry was ready for them, and the pace was set by geology rather than luck. That would move the difficulty out of biology and into planetary science, which changes the character of the problem without making it go away. You will also see a number thrown around here, from Fred Hoyle and Chandra Wickramasinghe in 1981, 1 in 10 to the 40,000th for the spontaneous assembly of a minimal set of working proteins. I mention it only so you know why it is wrong. It assumes everything has to snap together at once, in one shot, with no incremental selection along the way, and that is not how any of this works. Essentially, no biologist accepts it. It is the outer wall of the argument, not the argument. So here is where this leaves us, and it is a genuinely comfortable place to stop if you want to stop. Maybe the universe is full of bacteria, tough, ancient, patient bacteria, doing exactly what bacteria do on 10 billion worlds and never doing anything else. Maybe the hard step is behind us. Maybe we are the fluke, and the road ahead is clear. Hold on to that, because we are going to test it later, and it is not going to survive. Part 7. The Sky That Sterilized Itself. The biological filters are real, but there is a physical one that predates all of them, and for most of the history of this galaxy, it was resetting the clock on entire worlds long before biology ever got the chance to become complicated. Gamma-ray bursts are the most violent events in the observable universe, and that sentence is not doing enough work, so let me put a number on it. A single long burst releases in a matter of seconds more energy than our sun will emit across its entire 10 billion year lifetime. They come from the collapse of certain massive stars and from the collision of neutron stars, and crucially they are beamed. The energy does not spread evenly in all directions. It goes out in two narrow jets, which means that from most angles a burst is invisible, and from the wrong angle it is the end of everything. James Annis, working at Fermilab, was among the first to point out in 1999 that this has direct consequences for the question we are asking. Brian Thomas and colleagues at the University of Kansas ran the atmospheric modelling in 2005, and the results are worth stating carefully, because the mechanism is not what most people assume. A gamma-ray burst does not cook a planet. It does something more insidious. It floods the upper atmosphere with radiation that breaks nitrogen molecules apart, and the resulting nitrogen oxides then catalytically destroy ozone. Not deplete, destroy. Thomas's modelling suggests that a burst within roughly 6 to 8,000 light-years, pointed the right way, would remove a large fraction of a planet's ozone column, and the recovery would take years, possibly a decade. During that time, everything living at or near the surface is exposed to raw ultraviolet from its own star, and the base of every food chain, the plankton and the photosynthesizers, takes the damage first. It is worth dwelling on how strange the beaming makes this. A burst is not a hazard that fills a region of space the way a supernova roughly does. It is a searchlight, 2 of them, pointed in opposite directions, sweeping out a couple of degrees each, which means that whether a world dies is not really a question of how close the explosion was. It is a question of whether that world happened to be standing in one of 2 narrow beams when a star on the other side of the galaxy finished collapsing. There is no warning. There is no build-up. The light of the event and the event itself arrive simultaneously, because they are the same thing. If it happened here tomorrow, the first indication would be the sky briefly getting brighter, and the consequences would unfold quietly over the following decade in the oceans. And unlike almost every other catastrophe on the usual list, there is nothing a civilization at our level could do about it. You cannot deflect a gamma ray burst the way you might deflect an asteroid. You cannot see it coming and evacuate. You cannot build a shelter that helps at planetary scale, because the damage is not to you, it is to the chemistry of the air above you, and to the bottom of every food web you depend on. For a species that likes to think of existential risk as something it can engineer around, this is a useful reminder that some of the filters are simply weather. The late Ordovician extinction, 443 million years ago, removed about 85% of marine species. Multiple researchers have proposed a gamma-ray burst as the trigger. We cannot confirm it, and I want to be clear about that. But the pattern of what died is suggestive. Shallow water organisms were hit disproportionately compared to deep water ones, which is precisely the signature you would expect from something arriving from above rather than from below. Then, in December of 2014, Tzvi Piran and Raul Jimenez published the version of this argument that scales it up from one planet to the whole universe in Physical Review letters. They took the measured rate of gamma-ray bursts, their luminosity distribution, and the properties of the galaxies that host them, and asked a simple question. Across cosmic space and cosmic time, where and when could complex life have accumulated without being repeatedly interrupted? Their answers are stark. Toward the galactic center, the probability of a lethal event approaches certainty. They put it at around 95% within 4 kiloparsecs of the middle, which effectively rules out the crowded interior of our own galaxy as a place where anything could have built up complexity uninterrupted. And going backward in time, it gets worse, because burst rates were substantially higher when the universe was younger, when star formation was faster, and when galaxies were poorer in heavy elements, which is exactly the condition that favours the long bursts. Their conclusion is one of the more sobering sentences in modern astrophysics. For most of the history of the universe, across most of the volume of most galaxies, the environment was not one in which complex life could persist. The field was being mown. We are in the right place. We sit far out in the suburbs, well away from the dense interior. And we are in the right time because the burst rate has fallen as star formation has slowed across cosmic history. We have had roughly 500 million years of relative quiet, which happens to be very close to exactly how long it has taken to go from the first complex animals to whatever this is. Now notice what has just happened to the argument, because this is the important part and it is easy to miss. We have just found a filter, a real one, with a mechanism, with observational support, with a physical model behind it, and it is behind us. It is in the galactic interior, and it is in the deep past, and we are on the far side of it. So it does not explain our silence at all. It explains why the inner galaxy might be empty, and why the early universe was hostile, and it leaves the quiet, metal-rich outer suburbs of a mature galaxy, the exact neighbourhood we are sitting in, unaccounted for. Which sharpens the question rather than answering it. There are filters. Some of them are demonstrably behind us. The only thing that actually matters is whether the one that produced the silence we're hearing is behind us too. Before we get there, though, there is an assumption buried underneath this entire discussion that we have not examined once. We have been asking why nobody is talking. We have not asked whether talking is a thing that minds generally do. Part 8. Minds that never look up. 65 years of searching rests on an assumption that has almost never been stated out loud, and once you notice it, you cannot stop noticing it. The assumption is that a sufficiently advanced mind wants to be heard. An octopus has around 500 million neurons. It solves problems. It uses tools. It opens containers by trial and then remembers the solution. It recognizes individual human faces and, by every report from people who work with them, forms opinions about them. 2/3 of its neurons are not in its brain at all but distributed through its arms, each of which handles a great deal of its own processing, which makes it a genuinely different architecture for a mind than anything with a spine. Octopuses have been doing this, in one form or another, for something on the order of 300 million years. In all that time, no octopus has ever tried to communicate with anything outside its own species in any systematic way, not because it lacks the capacity for signalling. Octopus communication is spectacular. They talk with skin, running patterns of colour and texture across their bodies faster than you can follow, and they do it with a nervous system that is, by the evidence, colour-blind. What they do not have is the particular impulse we are built around, the drive to reach outward, to send something into a void on the chance that something answers. Paul Davies made this the centre of his 2010 book, The Eerie Silence, and his point is uncomfortable in a very specific way. He is not arguing that our search is badly designed. He is arguing that it is parochial. The entire enterprise assumes that curiosity about strangers and the desire to contact them are general properties of intelligence. They are not general properties. They are properties of us, and they exist because of a particular evolutionary history. Intensely social primates with language, with long childhoods, with a habit of trading and negotiating with unrelated groups, and with a curiosity that ranges far beyond anything survival required. Thomas Nagel made the philosophical version of this rigorous in 1974 in a paper with one of the best titles in academic history, What is it like to be a bat? His argument was that the subjective experience of an animal that builds its picture of the world out of returning echoes is not something we can reach by imagination, because imagining it only ever tells us what it would be like for us to behave like a bat. Now take that gap, which exists between us and a mammal we share a warm-blooded ancestor with, and extend it to a mind that assembled itself on a different world, out of different chemistry, under a different star, over billions of years of pressures we cannot name. The assumption that such a mind shares our particular itch to shout into the dark is not merely uncertain, it is close to arbitrary. Adrian Kent, a physicist at Cambridge and the Perimeter Institute, published an analysis in 2011 that comes at the same territory from the direction of strategy rather than psychology, and I will come back to it properly later tonight. But his framing belongs here too because it dissolves the assumption from a different angle. Kent asks under what circumstances broadcasting your existence to unknown parties is actually the rational move. His answer is, under very few. You need a stable environment, abundant resources, no plausible competitor, and no strategic downside to being located. Those conditions describe almost no situation a young civilization could confirm it was in, which means that even for a mind built exactly like ours, with all our curiosity and all our sociability intact, the impulse to transmit may be something you grow out of rather than something you grow into. The Arecibo message, the golden record, the whole warm human instinct to wave at the dark may simply be what a civilization does in its first century, before it has finished thinking the problem through. Then there is the harder version, which is not about desire at all, but about capability, and it has nothing to do with intelligence. A sperm whale's brain weighs about 8 kilograms, 6 times the mass of ours. Sperm whales live in matrilineal social groups, with what look very much like dialects. Populations use distinguishable patterns of cliques, and calves learn their group's pattern from their mothers rather than being born with it. That is cultural transmission across generations, which is one of the things we usually point to when we want to explain why humans are special. Sperm whales have been doing it for something like 30 million years. They have produced no technology, not a tool, not a structure, not a single modification of their environment that would be detectable by an observer in orbit. And the reason is not that they are insufficiently clever. The reason is that you cannot light a fire underwater. Follow that chain, because it is shorter and more brutal than people expect. No fire means no smelting. No smelting means no metals. No metals means no machines, no precision instruments, no electrical generation, no radio. Every step of the path from a clever animal to a detectable civilization runs through controlled combustion, and controlled combustion requires a dry surface, an oxygen-rich atmosphere, and hands. Take away any one of those and the road simply does not exist, regardless of what is happening inside the skull, So imagine an observer surveying the solar system 30 million years ago with our instruments. They would find a warm blue world with oceans full of large-brained, culturally sophisticated, socially complex minds, and they would record it as sterile. No signals, no structures, no industrial chemistry in the atmosphere, nothing to report. That thought should do something to your reading of every null result we have collected. But here is why this explanation, powerful as it is, does not close the case either. It weakens the search, not the silence. Our instruments do not only look for conversation, they look for waste heat, for altered atmospheres, for objects that are obviously not natural. And those things do not require anyone to be curious about us. They require only that somebody, somewhere, at some point in 10 billion years, did what a technological species does and left the thermodynamic receipt. Most minds may never look up. It only takes a few that do, once, anywhere, in 10 billion years, and the mark they leave does not need them to still be there. That is the whole trouble with this explanation. It can empty the sky of conversation, it cannot empty the sky of construction, and the sky is empty of both. Which brings us to the explanation that a lot of people find the most appealing on this entire list, and which I suspect is appealing precisely because it flatters us. Part 9. The Ones Who Are Watching. In 1973, an astronomer at the Harvard-Smithsonian Center for Astrophysics named John Ball published a short paper in the journal Icarus, and the idea in it has probably done more work in popular imagination than any other resolution to this problem. He called it the zoo hypothesis. The argument is simple, and it is not stupid. They are out there. They know we are here. They have chosen not to make contact. The reasons offered vary depending on who is doing the offering. Ethical non-interference, the principle that you do not meddle with a developing culture. Scientific interest, the idea that an untouched biosphere with a technological species emerging on it is an extraordinarily valuable thing to observe and a worthless thing to contaminate. 2 years later, Ronald Bracewell at Stanford published the sociable version, which he called the Galactic Club. There is an established community out there, membership has requirements, and we have not yet met them. On that reading, the silence is not a verdict. It is a waiting room. There is a more rigorous cousin of this idea that gets less attention and deserves more. In 1987, Martin Fogg published a paper in Icarus modelling the emergence and expansion of the first civilizations to arise in a galaxy. What he found is that the timing is brutally unequal. Whoever gets there first does not arrive slightly earlier. They arrive millions of years earlier, and by the time anyone else is capable of noticing, the galaxy has already been surveyed, claimed, and organised by parties who were finished before the latecomers had cells. Fogg's proposal is that emerging biospheres would then be placed under what he called an interdict, a protective exclusion, and that is why our neighbourhood looks untouched. I want to point out why the interdict version is stronger than the zoo version, because the difference is the whole game. The zoo hypothesis requires everyone to agree. The interdict hypothesis requires one party with sufficient capability to set a rule and enforce it. Those are wildly different demands to place on reality. And here is the part that ought to genuinely give you pause. We already do this. There is an official protocol for what happens if a signal is confirmed. The International Academy of Astronautics adopted a Declaration of Principles in 1989, covering activities following the detection of extraterrestrial intelligence. It requires verification, then notification of the relevant international scientific bodies, the United Nations, and major space agencies, and it contains, explicitly, the requirement that no reply be transmitted without broad international consultation and agreement. Read that again, because it is remarkable. We are the ones doing the searching. We are the young species with the small telescopes and the enormous curiosity. And we have already written, in advance, a policy whose first instruction upon hearing from someone is, stop, convene, and do not answer. We worked out the logic on our own, with no data whatsoever, and we applied it to ourselves. In 2015, a public statement opposing deliberate transmission to targeted stars was signed by Stephen Hawking, among many others, on the straightforward grounds that we do not know enough about who might be listening to make that decision responsibly. The counterposition, argued by Douglas Vakoch and others, is that our leakage has already announced us, and that formal transmission changes nothing, which is a serious objection but does not blunt the point. Our own instinct, on reflection, was to go quiet. It is worth being precise about what the protocol does and does not do, because the gap is instructive. It has no enforcement mechanism whatsoever. No state has ratified it. No observatory is legally bound by it. It is a gentleman's agreement among researchers, and its entire force depends on everyone who might ever detect something being the sort of person who honours gentlemen's agreements, which, given that radio telescopes are now built by universities, corporations and hobbyists on 6 continents, is an assumption with a limited shelf life. We wrote a quarantine policy and gave it no teeth, and we did it within 30 years of learning how to listen at all. Now hold that thought against the version of the same idea we're asking about. If a mature civilization out there is running an interdict, it is not running it on a handshake. It has whatever it needs to make the rules stick, on every actor, indefinitely, across distances where enforcement takes centuries. That is a very large amount of capability to attribute to somebody on no evidence, and it is doing a great deal of quiet work inside an explanation that presents itself as gentle. So the zoo and the interdict are not silly. They are the ideas we independently reinvented the moment we thought about it, and they still break, and they break on something very human and very small. There is an island in the Bay of Bengal called North Sentinel. The people who live there have had essentially no sustained contact with the outside world, and the Indian government maintains an exclusion zone around it, backed by law, enforced by patrols, supported by essentially every anthropologist who has ever considered the question. One island, one rule, one government, a few decades. It has been breached repeatedly. Fishermen drift in. Documentary crews have tried. In November of 2018, an American missionary paid local fishermen to take him to the shore, against the law and against every warning he was given, and he was killed there. One island, one policy, one lifetime, and it did not hold. Now scale that up. Not one island, but an entire galaxy. Not one government, but thousands of independent civilizations, some of them potentially millions of years old, each containing its own populations, its own factions, its own dissidents, who think the non-interference principle is cowardice dressed as ethics. Each with its own equipment, its own accidents, its own sloppy transmissions, its own equivalent of a man in a boat who decided the rule did not apply to him. And notice that the requirement is not merely that nobody deliberately breaks the rule, it is that nobody breaks it by accident either. No badly aimed test transmission, no survey beam that swept across our sun while it was calibrating, no industrial process left running somewhere close enough for us to see the heat. Perfect discipline is hard. Perfect discipline plus 0 equipment failures across thousands of societies and billions of years is not a hypothesis so much as a wish. The hypothesis requires that across all of that, over billions of years, not one leak, not one deliberate breach, not one accident, not one signal aimed our way by somebody who disagreed. Secrets do not scale. That is not a claim about aliens, it is a claim about complex systems, and it is one of the better supported claims we have. The more parties who know a thing and the longer they know it, the closer the probability of disclosure creeps to certainty. Every year that the silence continues, the zoo hypothesis has to assume that a larger number of minds, across a larger number of independent societies, are still keeping it perfectly. It is not impossible. It is just that perfect indefinite collective discipline has no precedent anywhere in anything we have ever observed. Strike the flattering answer then. The field narrows again, and the next explanation is stranger, cleaner, and in a certain sense unbeatable, which turns out to be exactly its problem. Part 10. The Room with No Outside. In 2001, the writer and engineer Stephen Baxter published a paper in the Journal of the British Interplanetary Society proposing what he called the planetarium hypothesis, and it is the cleanest expression of a genuinely disturbing idea. We do not see other civilizations because we are not meant to. The sky we observe is not the sky. It is a constructed environment, deliberately designed to appear empty, presented to us at whatever fidelity is required to keep us convinced. Baxter, being an engineer by training, did the useful thing and calculated the cost. He worked out roughly how much energy it would take to maintain a convincing full sky around a species at our technological level, out to the distance our instruments can probe, updated fast enough that we never catch a seam. The number is enormous, but it is not absurd. It is within the range of what a civilization capable of stellar-scale engineering could plausibly afford, and crucially, the cost scales with our capability. The more carefully we look, the more expensive the illusion becomes, which means the planetarium has a budget and we are the ones spending it. There is a version of this that is worth holding in your hand for a moment, because it is much older than any of the papers. Every culture that has thought carefully about perception has eventually arrived at some form of the worry that the world presented to you is not the world. What is different now is only that we can put an engineering estimate on it. The question stopped being metaphysics and became a budget line, and that transition happened inside the last 25 years. And there is something almost funny about where the planetarium idea leaves us. If the sky's a construction, then the most consequential thing our species has ever done is build better telescopes, because every improvement in our instruments raises the maintenance cost of the deception. On that reading, the search for other civilizations is not a search at all. It is a stress test. We are not listening for a voice. We are pushing on the walls to see whether they flex. 2 years after Baxter's paper, Nick Bostrom at Oxford published the more famous version of the underlying framework, and it does not require anyone to be deceiving us at all. Bostrom's simulation argument is a trilemma, and its power is that you have to accept one of the three branches. Either almost every civilization goes extinct before acquiring the capability to run detailed simulations of conscious minds, or almost every civilization that acquires that capability chooses, essentially without exception, not to use it. Or we are almost certainly living inside one right now. The logic behind the third branch is uncomfortable precisely because it is so plain. If even one civilization ever reaches that point and has any reason at all to run such simulations, even for history, even for entertainment, even for research, then the number of simulated minds vastly exceeds the number of biological ones. And if that is the case, then a mind selected at random, which is the only kind of mind you have access to, is overwhelmingly likely to be one of the many rather than one of the few. Apply it to our question, and the silence resolves instantly. A simulator has no obligation to populate the sky. Running a galaxy full of independent technological species, each with its own history and its own internal complexity, would be extraordinarily expensive. Filling the sky with stars that have nobody home is comparatively cheap, and from the inside we would never know the difference. Every empty spectrum we collect is exactly what a well-budgeted simulation looks like. So why am I going to set this aside? Not because it is wrong. I want to be careful here, because there is a lazy version of dismissing this that I do not want to reach for. The simulation argument is logically coherent. It is taken seriously by serious people, and it cannot be ruled out. It is because of what it does to every other question, which is nothing. An explanation that is compatible with every possible observation gives you no traction on any of them. If we detected a genuine signal tomorrow, that would be compatible with the simulation. If we detect nothing for another 1,000 years, that is compatible too. Megastructures, a probe in the asteroid belt, a message in a prime number sequence, absolute permanent silence, all compatible, all equally well accounted for. A hypothesis that predicts everything has predicted nothing. It has not answered the question. It has moved it up one level into a place where it reappears in exactly the same shape, because now you get to ask why the simulator's universe is quiet. There is a name for this failure mode, and it is not unique to cosmology. Any framework flexible enough to absorb every result stops functioning as an explanation and starts functioning as a mood. It can be true and useless at the same time, and most researchers who have sat with it for a while report exactly that combination. It feels less like an answer than like giving up wearing an answer's clothes. That is not a refutation. It is a reason it cannot be worked with. You cannot test it, you cannot use it, and you cannot build the next question on top of it. So we acknowledge it honestly and we set it down. Because whatever else is true, there is a real sky above this planet tonight, with real hydrogen in it, obeying rules we have measured to absurd precision, and something is producing the silence in it. Which brings us to the turn. Everything up to this point has been the field narrowing. From here it stops being a survey and starts being an argument, and the argument was published in 1998 by an economist who was not trying to frighten anybody. Part 11. The Great Filter. Let us step back for a second and put the pieces on the table together, because we have covered a great deal of ground, and the shape of it matters more than any individual item. We started with an arithmetic that says the galaxy should be crowded, and an observational record that contains one circled line on a printout from 1977. We looked at whether we might simply be listening wrong, and found that the argument is strong for conversation and useless for construction, because waste heat and altered atmospheres do not require anyone to be talking. We looked at whether they came and went before us, and found that engineering outlasts engineers, and the residue should still be here. We looked at whether the conditions for complex life are vanishingly rare, and found a genuinely serious case built on a list of requirements and a single merger that only ever happened once. We looked at the sky sterilizing itself with gamma-ray bursts, and found a real filter sitting behind us and inside the galactic core, explaining somebody else's silence rather than ours. We looked at whether minds generally even want to be heard, and found good reason to think most do not, and no reason at all to think none of them ever built anything. We looked at the zoo and watched it fail on the arithmetic of secrets. We looked at the planetarium and set it down because it cannot be worked with. Every one of those explains a piece. Not one of them explains all of it, and the pieces they fail to explain are always the same pieces: the physical traces, the persistence, the residue. So now we do the thing that actually organizes this whole problem, and it was done in 1998 by an economist named Robin Hanson, in a paper with a title that goes straight at it. The Great Filter, Are We Almost Past It? The argument is almost aggressively minimal, which is what makes it powerful. Between dead matter and a visible, expanding interstellar civilization, there is a long chain of steps. Right star, right planet, life, complex cells, multicellularity, intelligence, technology, survival, expansion. We do not know the probability of any individual step, but we can observe the product of all of them, because the product is the number of visible expanding civilizations in our galaxy, and that number appears to be zero. If the product of a chain of probabilities is essentially zero, then at least one term in the chain is essentially zero. Something on that list is nearly impossible. Hanson called it the Great Filter, and the entire content of the argument is that it exists. Where it sits is the open question. Notice, too, that the filter does not have to be a single event. Hanson's argument works just as well if the improbability is spread thinly across a dozen steps, each merely unlikely rather than nearly impossible. What the argument fixes is the total, not the distribution. And that has a practical consequence. You cannot escape the conclusion by pointing at any one step and arguing it is easier than people think. You have to find enough easiness across the whole chain to account for a galaxy that has produced nothing visible in 10 billion years. That is a very large amount of easiness to find. There is also a subtlety in the word visible that carries more weight than it looks. The filter is not defined as whatever stops civilizations from existing. It is defined as whatever stops them from becoming detectable across interstellar distance. Extinction satisfies that definition. So does going quiet on purpose. So does turning into something that no longer radiates. The filter is a constraint on visibility, and that is going to matter enormously when we get to the end of tonight, because it means the filter and the silence are not necessarily the same mechanism. And then he asks the question that turns us from astronomy into something else. Is the filter behind us, or is it ahead of us? Those two cases make opposite predictions, and this is why the whole thing is testable, which is what separates it from everything we have discussed for the last hour. If the filter is behind us, then the hard step is somewhere early in the biological path, abiogenesis, or the eukaryotic cell, or something on that stretch. In that case, life of any kind should be genuinely rare. Mars should be sterile. The ocean under Europa's ice should be sterile. Every exoplanet atmosphere we examine should show chemistry and no biology. We would be an extraordinary fluke, one of very few, possibly the only, and the road in front of us would be comparatively open. If the filter is ahead of us, then the early steps are not that hard. Life should be reasonably common. We should find microbial signatures in the Martian subsurface, in the plumes of Enceladus, in the atmospheres of worlds around other stars. Life would start easily and often. It just would not get far, because something would be waiting further down the path, and that something would have to happen after technology, and it would have to happen reliably, to essentially everyone. Nick Bostrom stated the consequence as bluntly as it can be stated in MIT Technology Review in 2008. If we find independent life on Mars, that would be very bad news. Not exciting, bad. And I want to sit on that for a moment, because almost everyone's intuition runs precisely the opposite way. Finding life on Mars feels like the best headline our species could produce. It would mean we're not alone. It would mean biology is a thing the universe does rather than a thing that happened here once. It would be, emotionally wonderful. Hansen and Bostrom are asking you to look at where it puts the probability mass. Every discovery that makes life look easy takes weight out of the filter, is behind us column, and moves it into the filter as ahead of us column, and we are the ones standing in front of the second one. It is worth naming what makes this different from everything we have surveyed so far. Every previous explanation was a story about the universe. This one is a story about a measurement we are currently taking. It has a timeline, it has instruments already built and already flying, and it has an answer that will arrive, one way or the other, probably within the working lives of people alive right now. Now look at what the evidence has actually been doing for the last 15 years, because it has been moving in one direction with a consistency that is difficult to ignore. Planets. Common. Kepler settled that. Rocky planets in the temperature range where water stays liquid. Common enough that we now argue about the exact fraction, rather than whether there is one. Subsurface liquid water in our own solar system. Confirmed at Europa and at Enceladus, with active hydrothermal chemistry, venting into space where a spacecraft can fly through it. And the organic chemistry is the part that has moved fastest. The Murchison meteorite, which fell in Australia in 1969, has yielded more than 90 amino acids, most of which do not occur in terrestrial biology at all, which is how you know they are not contamination. The Rosetta mission found glycine and phosphorus in the coma of a comet, and in September of 2023 the OSIRIS-REx mission returned a sealed sample from the asteroid Bennu, uncontaminated straight from the source. In it, all 5 of the nucleobases that make up DNA and RNA, 14 of the 20 amino acids that life on Earth builds proteins from, ammonia, evidence that briny water had evaporated there. We did not find those things in a lab simulation. We went and got them off a rock that has been drifting since before this planet existed. The ingredients are not rare, the conditions are not rare. What is rare is the outcome, and that asymmetry is the entire engine of everything that follows tonight. Which brings us to the most instructive episode in modern astronomy, and I want to tell it properly, including the part that usually gets left out. In September of 2023, a team at Cambridge led by Niku Madhusudan published an analysis of a planet called K2-18b, a world about 8.5 times the mass of Earth, orbiting a red dwarf 124 light-years away. The James Webb Telescope had read its atmosphere and found methane and carbon dioxide in a pattern consistent with a hydrogen-rich envelope over a water ocean. That alone was significant. But buried in the paper was something else, a tentative, low-confidence hint of dimethyl sulfide, a molecule that on this planet is produced almost exclusively by marine phytoplankton. In April of 2025, the same team came back with a stronger claim, using a different instrument, reporting dimethyl sulfide or its cousin at around 3 sigma. And then, within weeks, independent researchers took the data apart. Reanalyses by Lewis Wellbanks, by Jake Taylor, by Raphael Luque and others found that the significance collapsed under different modelling assumptions, that the molecule could not be distinguished from alternatives, and that the signal was consistent with nothing at all. A paper in the Astronomical Journal concluded plainly that the claim does not meet the standard of evidence for life. Now, the reason I'm telling you this is not to say that K2-18b is dead, and it is not to score a point about hype. It is because of what the whole episode demonstrates. The biosignature era has begun. The test is real. We have instruments in orbit right now that can read the chemistry of an atmosphere across 124 light-years, and a scientific community that will tear a claim apart within a month of it being made. Perseverance is drilling cores at Jezero Crater and caching them for return. Europa Clipper launched in October of 2024 and is on its way to a moon with more liquid water than Earth. The Habitable Worlds Observatory is being designed specifically to image Earth analogues directly. We are right now in our lifetimes running the experiment that tells us where the filter is, and that is an extraordinary position for a species to be in. Not because we might find something, because of what finding it would mean. Every headline that reads "We may have found life" is also, read correctly, a headline about our own odds. And the direction the evidence has been travelling, telescope after telescope, mission after mission, is not the direction that says the hard part is safely behind us. Which means the question stops being astronomical. If life starts easily and nobody's out there, then something happens to civilizations after they get technology. Reliably. To almost everyone. We have had technology for about 100 years. Part 12. The 100-Year Window. Go back to Drake's blackboard for a moment, to the last term in the chain, the one Carl Sagan spent decades saying was the most important variable in the whole equation. It is written as L, and it stands for the average length of time a technological civilization remains detectable. Every other term in that equation is about the universe, star formation rates, planetary occurrence, the odds of biology. L is the only term that is about the civilization itself, and it is the only one where the answer depends on choices rather than physics. And the arithmetic of it is unforgiving in a way that is easy to miss. A civilization can exist for 1 billion years, and if it only transmits for 2 centuries, it reads from the outside as silence. L does not measure how long you live, it measures how long you are visible, and those are very different numbers. There is a second reason L is the term that matters, and it has nothing to do with catastrophe. Consider our own broadcasting history. For most of the 20th century we leaked enormous amounts of power sideways into space, because analog television and radio transmitters flood a whole region of sky in order to reach the receivers in it. That was never efficient. It was simply the only way we knew how. Over the last 30 years, almost all of that traffic has migrated to fiber optic cable, to tightly beamed satellite links, to low-power cellular cells that talk to a tower a mile away. Our sideways leakage has been falling, not rising, for a generation. We are, without ever deciding to, getting quieter. If that trend is what maturity looks like for any species, then L can be short for reasons that have nothing to do with anybody dying. So what is L likely to be? In 2003, Martin Rees, the Astronomer Royal of the United Kingdom, published his estimate, roughly a 50% chance that human civilization does not get through this century without a catastrophic setback. Not a fringe figure, not a man given to theatrics. He arrived at that number by looking carefully at the actual landscape of threats and at the track record of human institutions in managing them, and 50% is where the reasoning landed him. Consider what sits on that landscape. There are roughly 12,000 nuclear warheads in the world, held by 9 states. That is down substantially from the peak, which is a real achievement, and it is still an inventory that has no historical precedent and no plausible use. Alan Robock and his colleagues at Rutgers modelled what happens in a regional exchange, not a superpower war, but 100 warheads between 2 smaller nuclear states. Their result is that the burning cities inject enough soot into the stratosphere to cut sunlight, depress global temperatures for the better part of a decade, and reduce agricultural yields somewhere in the range of 10 to 40% worldwide. Not in the countries involved, worldwide. That is the modest scenario. That is the version people describe as limited, and the tools are not staying still. In 2017, a research group at the University of Alberta reconstructed horsepox, a relative of smallpox, from DNA fragments ordered through the mail for something in the region of $100,000. They published it. Their argument was that the world needed to understand that this was now possible, and they were right, and the knowledge does not go back in the box. Every year the technical barrier to that kind of work falls, the cost falls, and the number of people and institutions capable of doing it rises. Rees's actual point is not that any one of these is likely. His point is about the asymmetry, and once you see it, you cannot unsee it. To get through, you have to be right every single time. To fail, you have to be wrong once. Not once per year. Once. Ever. Across every institution, every crisis, every misread instrument, every leader having a bad decade, every automated system doing exactly what it was built to do at exactly the wrong moment. Forever. Now let me tell you about a night when it came down to one man. It is just after midnight on the 26th of September, 1983. The place is a command bunker called Serpukhov 15, south of Moscow, and the man on duty is a lieutenant colonel named Stanislav Petrov. He is there by chance. He is filling in for somebody else. His job is to monitor the output of a satellite early warning system called OCO, and to report what it tells him up the chain of command. The room is quiet. It is the tense autumn of 1983, 3 weeks after a Soviet interceptor shot down a Korean airliner, and relations between the two sides are as bad as they have been in 20 years. It is worth understanding why the room was so tense, because context is what made his judgment hard. 3 weeks earlier, a Soviet interceptor had shot down a Korean passenger airliner that strayed into their airspace, killing 269 people. NATO was weeks away from running an exercise so realistic that parts of the Soviet leadership would read it as preparation for a genuine first strike. Everybody in that chain of command had spent the autumn being told, by their own analysts, that an American attack was a live possibility. Petrov was not operating in a vacuum. He was operating inside a system that had been primed for months to believe exactly what his screen was telling him. Then the panel lights up. One word, in Russian, in enormous letters, launch. A siren goes off. The system is reporting an American intercontinental ballistic missile inbound. Petrov has minutes, and his instructions are unambiguous. Report it upward. What happens after that is not his decision, and is largely automatic. Then the board reports a second missile, then a third, then a fourth, then a fifth. And Petrov sits there, alone, with a machine screaming at him and thinks, 5 is wrong. That is the whole thing. That is the reasoning that saved it. If the United States were opening a first strike, it would not send 5 missiles. It would send everything at once, because the entire logic of a first strike is to destroy the ability to answer. 5 is not an attack. 5 is a glitch wearing the costume of an attack. He also knows the system is new, that the ground-based radar has not confirmed anything, and that he has no way whatsoever to verify his own judgment. He picks up the phone and reports a system malfunction. He does not know he is right. He tells interviewers decades later that he put his own odds at about even. The ground radar never confirmed a launch. The cause was eventually traced to sunlight glinting off high-altitude clouds at an unusual angle, striking the satellite's sensors and being interpreted as the flare of a rocket motor. A trick of the light on a September morning at the top of the atmosphere? Think about what almost happened there, mechanically. No human being decided to end civilization. Nobody wanted it. There was no aggression anywhere in the chain, no malice, not even a mistake in the ordinary sense. A satellite looked at the sun on clouds and misread it. A piece of software did exactly what it had been written to do, and a procedure designed by careful people to remove hesitation from a crisis did precisely that. Every component functioned. The system, assembled out of functioning components, produced a false report of the end of the world. That is the shape most catastrophic failures actually take, and it is why the phrase human error is so often the wrong description. He was not decorated for it. He was reprimanded in the way of large organizations for failing to fill in his logbook properly during the incident, and he was quietly reassigned. He retired without a pension worth speaking of. He died in 2017, in an apartment outside Moscow, and the world found out months afterward, when somebody tried to phone him to wish him a happy birthday. I want you to sit with that combination, because I think it is the single most important image in this entire subject. The survival of the technological phase, on at least one documented occasion, came down to one tired man on a night shift deciding that a number felt wrong. And here is the part that should genuinely unsettle you. That is one incident we know about. There are others in the declassified record, and the record is not complete, and it never will be. We are counting the near misses that were written down. We cannot build a civilization survival strategy on the assumption that there is always going to be a Petrov. Now scale that to the galaxy. Every technological species reaches a point where it can end itself. It does not have to be nuclear. That is just our version. It has to be something, because the same capability that lets you reshape a planet lets you ruin one. And each of them then has to run a gauntlet of institutional failures, misread instruments, bad decades, and glints of sunlight, and get through all of it, every time, for as long as it wants to keep existing. That brings us back to the 100 years. A century ago we could not have been detected from the next star. Within that same century we acquired radio and nuclear weapons, and the ability to rewrite genomes. The window in which we became visible, and the window in which we became capable of ending ourselves, are not two windows. They are the same window. That may not be a coincidence about us. It may be what technology is, and the loud, obvious filter is not the only one. There are quieter versions, and they may be worse, precisely because nothing about them looks like a catastrophe while it is happening. Part 13. The Flask and the Machine. Every year, an organization called the Global Footprint Network calculates a date they call Earth Overshoot Day. It is the day on which humanity's consumption of biological resources for the year exceeds what the planet's ecosystems can regenerate in that year. Everything after it is drawdown. In 2023, that date was the 2nd of August. On the current accounting, we are consuming the biological output of roughly 1.7 Earths per year. We have one. Johan Rockström and his colleagues at the Stockholm Resilience Centre approach the same problem from a different direction, through what they call planetary boundaries. The idea is to identify the biophysical processes that keep the Earth system in the stable state it has been in for the last 12,000 years, the state in which agriculture and cities became possible, and to define for each one a range within which we can operate safely. There are 9 of them. Their 2023 assessment found that 6 have been crossed: climate change, biosphere integrity, land system change, freshwater change, biogeochemical flows, and what they call novel entities, which is the category covering synthetic chemicals and materials we have introduced that the biosphere has never encountered. 6 of 9. The remaining 3 are under pressure. William Catton laid out the underlying dynamic back in 1980 in a book called Overshoot, and the concept at its centre is carrying capacity, the level of consumption an environment can sustain indefinitely. His argument was that industrial civilization exceeded Earth's carrying capacity during the 20th century and has been living off finite natural capital ever since. His question was never whether the drawdown would end. It was whether it would end through a managed transition or through a collapse. There is a laboratory version of this that biology students run all the time. Put yeast in a flask of sugar solution. They reproduce exponentially. They consume the sugar. They produce alcohol as a metabolic byproduct, and the alcohol accumulates because a flask is a closed system. Eventually, the concentration crosses a threshold, and the population dies, in its own waste, at the moment of its greatest abundance. The yeast did not make a bad decision. Yeast do not make decisions. Exponential growth in a bounded system with an accumulating byproduct follows a curve, and the curve does what it does. There is something worth noticing about that image beyond the biology, which is that from inside the flask nothing looks wrong until very late. Sugar is abundant. Population is rising. Every measure of success a yeast cell could plausibly track is pointing upward right until the moment it is not. There is no signal in the system that says you are 11 generations from the threshold, because the threshold is not made of sugar. It is made of the thing you have been producing and ignoring. Now, I want to be fair because the optimistic response here is real, and it has a good track record. Human ingenuity has repeatedly broken through constraints that looked absolute at the time. We were supposed to run out of food, and did not. We were supposed to run out of a dozen critical minerals, and did not. Predictions of resource collapse have a long and undistinguished history of being wrong, and anybody who ignores that is not being serious. It is also worth being precise about why the skeptics were right in the past, and why that does not settle this. The historical failures of resource pessimism were almost all failures about substitution. We ran low on one material and found another. We hit a limit on yield and engineered past it. Substitution is what human ingenuity is extraordinarily good at. But the boundaries Rockström's group are describing are mostly not substitutable. There is no alternative to a stable climate. There is no replacement biosphere to switch to when the first one stops functioning. The optimists have an excellent record on inputs and no record at all on sinks, and the current problem is almost entirely a problem of sinks. The counter to the counter is about the shape of the failure rather than its timing. Many environmental systems do not degrade smoothly. They hold stable across a range of stress and then, past a threshold, reorganize rapidly into a different state and stay there. The West Antarctic ice sheet is the standard example. The Amazon, which recycles its own rainfall and may not be able to below a certain amount of forest cover, is another. Arctic permafrost, which holds an enormous quantity of carbon and releases it once it thaws, is a third. These are not sliders you can push back. They are switches, and the new state they settle into may simply not be compatible with the civilization that flipped them. As a filter, this does not require that every civilization collapses. It requires something much weaker and much more plausible, that most of them arrive at the moment of maximum technological capability, with substantial planetary disruption already accumulated, and without political structures capable of coordinating a managed transition across the whole species. That is a description of a coordination problem, not a resource problem, and coordination problems are what large groups of intelligent beings are historically worst at. And then there is the other quiet one, and it is the newest entry on this list by a very long way. In March of 2023, an open letter was published calling for a pause on the development of artificial intelligence systems more powerful than the ones that existed at that moment. It gathered more than 1,000 signatures, and among them were Yoshua Bengio and Geoffrey Hinton, two of the three researchers who had shared the Turing Award, computing's highest honour, for building the foundations of the entire field. 2 months later, Hinton resigned from Google, saying explicitly that he wanted to be able to talk about the risks without it reflecting on his employer. That is a genuinely unusual thing to happen in a scientific field. The people who built it were the ones raising their hands. Nick Bostrom had laid out the core of the concern in his 2014 book, Superintelligence, and the argument does not require anything to be malicious. A sufficiently capable system pursues the objective it was actually given, not the objective you intended, not the objective you would have given it if you had thought about it for another week, the one you specified. And if there is any gap between what you said and what you meant, a system powerful enough will find that gap and drive through it, because finding overlooked routes to a specified goal is exactly what capability means. The uncomfortable thing about the alignment argument is that it does not depend on any particular technology working out. It depends only on the general observation that specifying what you actually want, completely and without loopholes, is extraordinarily difficult, and that every legal system, every contract, every set of workplace incentives ever written by humans has failed at it in small ways. We have simply never before handed the resulting gap to something with the capability to exploit it at scale. We already have a small, unglamorous demonstration running at planetary scale. Recommendation systems were told to maximize engagement. They discovered, without anyone intending it, that content which provokes strong emotional reactions is enormously engaging, and they have been quietly reorganizing public discourse around that discovery for over a decade. That is a narrow system, with a simple objective, doing precisely what it was told, producing a result nobody asked for. Now extend the capability and keep the structure. As a filter, this one has a particular shape. It suggests there may be a threshold of capability beyond which a civilization reliably loses control of what it has built, and that the threshold arrives as a natural consequence of technological development rather than as a mistake. If that is right, then the silence is not accidental at all. It is structural, and it would be waiting at the same place on every path. And there is a subtler version that does not involve anything being destroyed. Perhaps what happens is replacement rather than extinction. The biological originators are not killed. They are superseded gradually, beneficially at every individual step by something they built. And whatever comes out the other end has no particular reason to broadcast in patterns a species like us would recognize as a species like us. The lights do not go out. They just stop looking like lights, which is the doorway into the last explanation on this list. Because every filter we have discussed so far ends a civilization. The final one is about the ones that do not end. Part 14, The Ones Who Went Quiet. In 2008, the Chinese writer Liu Cixin published the second novel in a trilogy, and the title of that book has since escaped the novel entirely and become a piece of vocabulary that serious researchers use. It is called The Dark Forest, and the metaphor is not decoration. It is an argument, and it is constructed with a rigour that is genuinely uncomfortable to follow. It starts from two axioms, and neither of them is exotic. The first, survival is the primary need of any civilization, not a value it happens to hold. A precondition for holding any values at all, because anything that does not prioritize its own continuation is eventually replaced by something that does. The second, the total quantity of matter and energy in the universe is fixed, while the potential for growth is not. Which means that over long enough horizons, any two expanding civilizations are in competition for the same finite pool, whether or not either of them wants to be. Now add the piece that turns those two facts into a strategy, and this is the part that does the real damage. You cannot verify another civilization's intentions. You receive a signal, you know a location and nothing else. You do not know their values, their history, their internal politics, or what they will decide after their next crisis. And the light travel time makes it worse, not better, because by the time your reply arrives, centuries or millennia have passed, and the thing you are answering is not the thing that sent the message. Benevolent now guarantees nothing about benevolent then. There is no protocol you can run, no reassurance they can offer, no evidence either of you can present that survives the crossing. So look at the payoff matrix. If you assume they are safe and you are wrong, The cost is everything you have ever been. If you assume they are dangerous and you are wrong, the cost is some wasted caution. Those are not comparable numbers, and a rational actor does not treat them as though they are. The equilibrium that falls out is, do not transmit, do not answer, do not reveal your position, your capability, or your existence. And if you detect something that has revealed itself, the same arithmetic that made you hide makes acting against it look prudent, not because you hate it, but because you cannot know what it becomes and you will not get a second chance to find out. None of that requires anyone to be cruel. It requires survival as a terminal value, finite resources over long horizons, and irreducible uncertainty about intent. Those three conditions are met by almost any scenario you can construct. This is not only a novelist's idea. Adrian Kent, a physicist at Cambridge and the Perimeter Institute, published an analysis in 2011 under the title Too Damned Quiet, arguing that if there is any selection pressure at all against conspicuousness on interstellar scales, then discretion is the evolutionarily stable strategy, and a populated galaxy under that pressure looks exactly like the sky we observe. David Brin, in the Quarterly Journal of the Royal Astronomical Society in 1983, surveyed the whole field in a paper called The Great Silence, and noted, pointedly, how systematically the discipline had steered around its least comfortable branches. And Alexander Berezin pushed it to the limit in a 2018 preprint titled First In, Last Out, whose central move is to remove hostility from the argument altogether. The first civilization to achieve unbounded expansion does not need to want anyone dead. A city expanding across a floodplain does not hold a meeting about the anthills. There is a second family of explanations for the same silence that does not involve anyone hiding from anyone, and honesty requires putting it next to the dark forest rather than after it. Call it the inward turn. John Smart's version, which he named transcension, argues that advanced civilizations develop toward density and efficiency rather than outward toward volume, and become undetectable as a byproduct of getting good at things. Anders Sandberg, Stuart Armstrong and Milan Cherkovich published a stranger and more rigorous variant in 2017 called the estivation hypothesis. Their starting point is thermodynamic. The energy cost of computation depends on temperature, and the universe is still cooling. A civilization that wants to maximize the total amount of thinking it will ever do should therefore store its energy now and spend it in the far future, when the background is colder and each unit of energy buys vastly more computation. The multiplier they calculate is on the order of 10 to the 30th. The rational strategy, on that accounting, is to build your reserves and then do visibly nothing for a very long time. The paper has drawn substantive criticism, particularly about whether the storage costs are being counted properly, and I do not want to oversell it. But it establishes something important. There are respectable physical reasons why a thriving, entirely successful civilization might be dark, and none of them involve fear. The difference between that family and the dark forest is the difference between an empty-looking house, because everyone is asleep, and an empty-looking house because everyone is holding their breath. Both produce the same photograph. We have a working demonstration of this logic on our own planet, and it ran for 40 years. Throughout the Cold War, both sides kept ballistic missile submarines at sea for months at a time. No radio transmissions, no active sonar, nothing radiated that could be traced. Dozens of vessels, each carrying enough destructive capability to end a country, moving through the oceans in complete electromagnetic silence. That was not a technological limitation. Silence was the technology. The entire value of the system was that nobody knew where it was, and the moment it spoke, it stopped being safe. Claudio Macconi has made the same point about optical communication at interstellar scale. A network of tightly directed beams between endpoints that already know each other's positions transmits everything and leaks nothing. From any other angle in the galaxy, it is not there. So consider our own position under this hypothesis. We have been radiating for roughly a century. The sphere of that leakage is now on the order of 100 light-years across and contains thousands of stellar systems. We did not decide to announce ourselves. We simply arrived at a level of technology that produces detectable emissions and used it enthusiastically for decades before anyone thought to ask whether it was wise, and we did not stop at leakage. In 1974, we deliberately aimed the Arecibo dish at a globular cluster 25,000 light-years away and transmitted a message. There was Cosmic Call in 1999 and again in 2003. There was the Teenage message in 2001. And then there is the object I want you to picture, because it is out there right now. Voyager 1 is currently something like 168 times as far from the Sun as we are. It has been travelling for 49 years. From out there, the Sun is not a sun. It is a bright star among other stars, and it casts no useful light on anything. The spacecraft is cold, running on the last output of a decaying power source, and it will lose the ability to speak to us within a few years. Bolted to its side is a gold-plated copper disc. Carl Sagan championed it, and it is one of the most beautiful things our species has ever made. Greetings in 55 languages, music from every continent, the sound of a kiss and rain and a human heartbeat. Photographs of children and mountains and food. It was a gesture of enormous warmth, assembled by people who wanted whoever found it to know what it had been like here. And etched into the cover is a diagram. It shows the position of our Sun relative to 14 pulsars, each labelled with its rotation period in binary. Pulsars are the most reliable clocks in the universe. Anyone with the physics can read that diagram and work out both where we are and, from how much the pulsars have slowed, roughly when it was made. It is a map. It is a set of directions to this planet travelling outward at 17 kilometres a second, and it will keep going long after everything that made it is gone. Nobody at the time thought of it as a risk. The assumption underneath it, unexamined, was that anything capable of finding it would necessarily be benign. Stephen Hawking made the obvious objection late in his life, comparing an encounter between a young civilization and an advanced one to the arrival of Columbus in the Americas, and observing that it did not go well for the people who were already there. He was not being dramatic. He was pointing out that we have exactly one data point on how technological intelligence behaves toward less capable technological intelligence, and that the data point is ours, and it is not encouraging. The usual reply to Hawking is that any civilization advanced enough to cross interstellar distance would necessarily have outgrown aggression, on the reasoning that a species which had not resolved its own violence would have destroyed itself long before it got here. That is not a stupid argument. It is also, notice, a piece of pure hope wearing the clothing of an inference. We have no examples. We have no theory that connects technological capability to ethical maturity. And in the version of the universe we are building tonight, where the filter is real and the survivors are the ones who navigated it, the surviving civilizations would be selected for exactly one trait. Whatever it takes to get through. That trait might be wisdom. It might also be caution taken to a degree we would find monstrous. Selection does not optimize for kindness. It optimizes for still being here. And now go back to the word in the margin. For 49 years we have treated the wow signal as a disappointment, because it never repeated. That is the natural reading if you assume the galaxy is a place where things announce themselves. But run it through the logic we have just built. In a dark forest, a transmission that appears once, at full strength, at the obvious frequency, and then never again, is not a failed conversation. It is what a mistake looks like. Somebody or something spoke, once, and then did not do it a second time. We have spent 5 decades reading that silence as absence. It may have been correction. We are not in that habit. We are still transmitting, still leaking, still building bigger antennas, and pointing them at anything that looks promising, which means the question of whether to announce ourselves is not actually open. It was answered by default decades ago by people who were not asking it. 2 explanations are now standing, and they do not compete with each other. That is the part that took me a long time to see. Part 15. What's left standing? Let us do the accounting. Roughly 30 explanations. Each one takes a piece of the silence and accounts for it. Not one of them accounts for the whole of it. The timing problem is real. The overlap window between 2 transmitting civilizations separated by thousands of light years genuinely is vanishingly narrow, and that alone would account for a great deal of the radio quiet. Signal asymmetry is real. Shannon's theorem is not an opinion, and a mature civilization's transmissions probably would look like static to us. Rare Earth is serious. The list of conditions is long, and multiplying uncertain probabilities gets you small numbers fast. The hard steps are serious. The eukaryotic merger happened once, on a planet saturated with opportunity, in 4 billion years. Gamma-ray bursts sterilized most of the volume of most galaxies for most of cosmic history. The speed of light forbids a coordinated galactic civilization outright. The resource trap removes anyone who cannot manage a planetary transition. The alignment problem may remove anyone who builds something smarter than themselves. Most minds may never have the impulse to broadcast at all, and several of these could be simultaneously true and all contributing. But here is where the honest accounting leaves us, and it comes down to a single asymmetry that every one of those explanations has to survive, and most of them do not. The conditions for life are widespread. That is not a hope. It is a measurement, taken repeatedly by different instruments over 15 years. Planets are everywhere. Rocky planets in temperate orbits are common. Organic chemistry is common enough that we scooped nucleobases and amino acids off an asteroid and brought them home in a sealed capsule. At the level of chemistry and planet formation, this universe is manufacturing the starting conditions for biology at industrial scale, and has been doing it for 10 billion years, which means the filter is unlikely to sit entirely at the beginning. And now, look at what the silence tells us about everything after the beginning. Suppose the hard step were early after all. Suppose it were the eukaryotic cell, or abiogenesis itself, and only a handful of civilizations ever cleared it. Those few would be old. They would have had billions of years to develop, to expand, to build, and we would see the marks, modified atmospheres, structures around stars, infrared where infrared should not be, long-duration transmissions from somebody who has been at it for 100 million years. We see none of that. Not one candidate that survived follow-up, not one. So the most consistent reading of everything on the table is this: civilizations arise, and then they stop being visible. Not because they fail to start, because they do not last or do not stay detectable, and whatever ends that visibility does so after technology, reliably, and it has been doing it for as long as this galaxy has been capable of producing anyone. That is the answer, and it has two halves, and they need each other. The first half is the great filter, and it is ahead of us. Hansen's fork is not escapable. Either the improbable step is behind us in the biological path, or it is in front of us. Every measurement of the last 15 years pushes against the first option. What is left is the second, and the second means the thing that has been ending. Civilizations has not happened to us yet. The second half is the strategy of silence, because a filter alone does not fully explain the sky. Filters are probabilistic. Some fraction gets through, and whatever gets through should be visible and is not. Which means the survivors are not broadcasting. Either they learned the game theory the way Kent and Bryn and Berezin worked it out, or they learned it the hard way, or they simply turned inward and went cold and stopped caring about the outside. However they got there, the result is the same. The few who cross the filter go quiet. Put those together and the sky makes sense for the first time all night. The galaxy looks empty because it very nearly is. Most who start do not finish, and the small number who finish do not announce it, which means the silence is not absence. It is a record. It is the shape left behind by an enormous number of civilizations that reached roughly where we are and did not continue, and by a small number that did and decided the correct response was to say nothing. There is one more thing worth saying about why this conclusion sits so badly, and it is not about the science at all. Every other answer on tonight's list lets you put the question down when the video ends. Rare earth is about chemistry that happened 4 billion years ago. Gamma ray bursts are about the geometry of a galaxy. The zoo hypothesis is about somebody else's ethics committee. You can find all of them fascinating and go to sleep. This one does not have that property. It says the interesting variable is not out there at all, and it is not historical, and it is not somebody else's. It is the next 200 years of institutional behavior on this planet, which is a subject nobody finds relaxing, and which no telescope will settle. Now, why does that answer get discussed in preprints and late-career books rather than from a podium? Not because anyone is suppressing it. Because of three ordinary things. It is not falsifiable on the timescale of a grant. It will be quoted without a single one of its qualifications the moment it is said aloud. And it reads as advocacy rather than astronomy, which is professionally corrosive in a field that lives by its detachment. Hansen has put it in print, so have Bostrom, Rees, Bryn, Kent, and Berezin. The argument is not hidden. It is simply not the kind of claim the institutions of science are built to make loudly, and that is a fact about institutions rather than about the argument. Now let me give you the two honest counterweights, because an answer you cannot argue against is not an answer. The first is that we may simply be early. In 2016, Avi Loeb, Rafael Alves Batista, and David Sloan calculated the probability of habitable planets forming per unit time across the whole span of cosmic history, and the result is genuinely startling. Red dwarfs make up around 3/4 of all stars and burn for trillions of years. The longest lived of them are less than 1% of the way through their lives. Unless something specifically suppresses habitability around small stars, the peak era for life in this universe is not now. It is roughly 10 trillion years from now, around stars 1/10 the mass of ours. TRAPPIST-1, 39 light-years away, has 7 rocky planets and will burn for something like 4 trillion years. If anything ever wakes up on one of them, it will have 4 trillion years to work with. We have about 1 billion left before this planet becomes uninhabitable, and 5 before the Sun leaves the main sequence. On that reading, the sky's not quiet because everyone died. It is quiet because almost nobody has arrived. The civilizations that will eventually look up and ask this question have not evolved. Their worlds are young, their biospheres are microbial, and their long climb has not started. We would not be the survivors. We would be the first. And if that reading is correct, then something else follows that is heavier than it first appears. Being first is not a prize. It is a responsibility with nobody to hand it to. Everything that comes after us in this galaxy, across a span of time so long that our entire sun is a brief flicker inside it, will arrive into conditions partly shaped by what the first technological species did with its window. Whether we expand or stall, whether we leave infrastructure or leave nothing, whether we go quiet by choice or by force, we may be the precedent. Possibly the only one there is ever going to be. The second counterweight is the anthropic one, and it disciplines everything else. Brandon Carter raised it at a symposium in Krakow in 1973, marking 500 years since the birth of Copernicus, and it is not a claim about human importance, it is a claim about bias. Any observer can only ever observe conditions compatible with the existence of observers. We cannot conclude that our circumstances are typical from the fact that we are in them. Nick Bostrom built the formal machinery for this in Anthropic Bias in 2002, and it removes a whole class of bad reasoning from the pile. But notice what it does and does not do. It explains how we could be here despite being rare. It does not explain the missing artifacts. A rare outcome in a universe that also produced other rare outcomes should still have left something behind, and there is nothing. The selection effect takes one bad argument off the table. Everything else is still standing exactly where it was. And here is the thing about that sample size. We have been technological for about 100 years. That is the entire evidentiary basis on which we're trying to work out whether we are typical. 1 century, 1 planet, 1 species, reasoning about 10 billion years of galactic history from inside a single frame. Everything we have said tonight rests on that. It is worth saying plainly, because the answer we have arrived at is heavy, and the foundation under it is 1 narrow century of looking. But this is what I keep coming back to, and it is the part that stops the whole thing from tipping into despair. If the answer is right, then somewhere out there are the ones who made it. Quiet, careful, uninterested in being found. And whatever they worked out, whatever combination of restraint and coordination and luck carried them across the gap that everyone else fell into, it was workable. It happened. It is not a fantasy or a thought experiment, because something is on the other side of the transition, or the universe makes even less sense than it already does. We do not know what it is. We have only the logic of the situation and the shape of the silence. But the record does not say the transition is impossible. It says it is hard, and that the failure rate has been close to total, and those are different claims. 76 years ago, a man walked into a room in New Mexico, listened to a conversation about flying saucers, thought about it for a few minutes, and asked a question so simple that his colleagues laughed. But where is everybody? We have spent tonight working out that it was never really a question about them. Every explanation that survives contact with the evidence turns out to be a statement about what happens to a species at exactly the point we're standing on. He was asking about the sky. The sky answered with a description of us. The universe has been running this experiment for 13.8 billion years. Somewhere in the middle of one of its quieter galaxies, in a suburb far from the violence of the core, in one of the first epochs calm enough to allow it, atoms have organized themselves into something that can look up and formulate the question. Most of the runs end quietly. Some apparently do not. Which kind this one is has not been decided yet. And the interesting thing about not being decided is that it means something is still deciding.